Okay, so here's a case where logarithmic differentiation can be helpful for us to take the derivative. And so notice that this isn't a log right here, but I also notice when I take the derivative of this, it's gonna be nasty. I have that square root. So I notice I am gonna have to use my chain rule, but underneath that inner function, I notice that I have a product, and then I also have a chain rule in there. So just a lot of different rules going on and more room for error. So let's rewrite this. We know that if we take the log of both sides, or natural log of both sides, if we do something to one side, we can do it to the other. And so let's take the natural log of the right-hand side, y, is equal to the natural log, and I'm using natural log because those were easier to differentiate, times this other side. And at the same time, maybe let's rewrite the square root. We know we can rewrite that as a 1/2 power. And so let's do that. That's a natural log of this x squared plus 1 all times x minus 1 quantity squared. And this is all raised to the 1/2 power. So the reason why I'm taking the log of both sides is I can use rules of logs to break this down into simpler pieces. I know with this 1/2 power, I can bring this down in front. So this is the same thing. So natural log of y is equal to 1/2 times the natural log of this x squared plus 1, that parentheses times x minus 1 quantity squared. So rules of logs that we reviewed in that last video, we have multiplication. So log, and we're multiplying, we can break that up as a sum of logs. So this is 1/2. You need to be careful here because this is parentheses or brackets around this. The natural log of the first piece, x squared plus 1, plus, times make it plus, the natural log of the second piece, which is x minus 1 quantity squared. And I need to bring down both sides. So I can clean this up a little bit more if I wanted to. I notice that the square on that second natural log, I can bring that down front of that log. And so that would be the same thing as 2 natural log of x minus 1. And if we really want to, and I probably would, let's distribute that 1/2. So the natural log of y is equal to 1/2 the natural log of x squared plus 1. Well, 1/2 times 2, that's going to cancel, so we're just left with a natural log of x minus 1. Now let's take the derivative of both sides. So we're going to use implicit differentiation, because notice we have a term y here. It's not just y equals. So now use implicit differentiation. So taking the derivative of the natural log of y, well, natural log of x was just 1 over x, but the natural log of y, that would be 1 over y. But y is a function of x, so that's where we had to tack on the dy dx. This is equal to 1/2 our coefficient, leave it alone. Now let's take the derivative of this natural log of x squared. So it's always, it's always 1 over, when it's a natural log, of what you're taking the derivative of, or natural log of, which is x squared plus 1, times the derivative, I'm just going to write it, d dx of the inside, x squared plus 1. So plus, now let's take the derivative of this natural log of x minus 1. Well, for natural logs, it's 1 over what you're taking the natural log of, which is x minus 1, times the derivative of x minus 1. So we have 1 over y dy dx is equal to, let's look at this. So this would be the same thing as 1 all over 2. I can put this 2 down in here, but I need parentheses around the x squared plus 1 and times the derivative of x squared plus 1. Well, that's equal to 2x plus 1 over x minus 1 times the derivative of x minus 1, which is just 1. So I notice in my first fraction on the right-hand side, I have a 2 in the numerator denominator factors that are the same that we can cancel. We're almost there. We have 1 over y dy dx equals x all over x squared plus 1 plus 1 over x minus 1. The problem is we wanted the derivative. We didn't want the derivative 1 over y times the derivative. And so all we have to do is to get this derivative by itself, we need to multiply both sides by y. So those y's cancel, and we're left with the derivative dy dx is equal to this x all over x squared plus 1. We could get a common denominator if we wanted, plus 1 over x minus 1. Instead of writing y though, y was this. And so instead of writing y here, we're going to write what the equation was, which was the square root. So times the square root of x squared plus 1, all times x minus 1 quantity squared. So this is where using logarithmic differentiation, taking the logs of both sides, natural log, log base e, and then breaking down that messy log that you'll get on the right-hand side using rules of logs as a sum or difference of logs can make our life so much easier. Questions on that one? Okay, so here's an example where you would want to use logarithmic differentiation to take the derivative of this. This would be really ugly, having to apply the product rule multiple times in the numerator, product rule in the denominator, chain rule, quotient rule. So let's use logarithmic differentiation. Let's take the natural log of both sides. And as I take the natural log, I'm going to rewrite that cubed root as the 1/3 power. So x all times x plus 1, all times x minus 2, all over x squared plus 1, all times 2x plus 3. And this is raised to the 1/3 power. So now we're going to start breaking this down. I'm going to leave the natural log of y there for now, and then we'll bring it back down later. So we can use rules of logs, and we can bring our exponent down front. So this is the same thing as 1/3 natural log of x all times x plus 1, x minus 2, all over x squared plus 1, all times 2x plus 3. So notice now we have division. Division, we can break up logs with subtraction in between. And so we have this 1/3 natural log of the numerator, which is x times x plus 1 times x minus 2. And then we need brackets here. We have this minus the natural log of x squared plus 1 times 2x plus 3. So notice that that first grouping of natural logs, there's multiplication in between 3 of those things. So we can break that down as the sum of 3 different natural logs. So we still have this 1/3 out front. Here we were going to have our natural log of the first piece, ln of x, plus the natural log of the second piece, natural log of x plus 1, plus the natural log of the third piece in the multiplication, natural log of x minus 2. You need to be careful because this minus sign is going to be distributed. So we need parentheses around when we break up this natural log of this multiple. So this is going to be the natural log of the first piece, x squared plus 1, plus the natural log of 2x plus 3. Here down natural log of y. So it looks like I'm now in the place that I can take the derivative of this. So going through and taking the derivative, I'm using implicit differentiation. Taking the derivative of 1 over y is 1 over y dy dx. Equals, I'm just going to leave my coefficient alone and take the derivative of the inside. Well, the derivative of natural log of x, that's just 1 over x, plus the derivative of the natural log of x plus 1 is 1 over x plus 1, times the derivative of the inside, but the derivative of the inside, I'm just going to put a 1 here, is just 1, plus the derivative of natural log of x minus 2 is 1 over x minus 2 times the derivative of the inside, but that's just 1, minus the natural log of x squared plus 1. That's 1 over x squared plus 1 times the derivative of the inside, though. So derivative of this inside would be 2x. Plus, actually not plus, because of this negative sign, it has to be distributed. So really minus the derivative of the natural log of 2x plus 1 is 1 over 2x, and that's 2x plus 3, not 1, 2x plus 3, times the derivative of 2x plus 3, which is 2. I'll back it down. And we're almost there. They might want you to get common denominators, I'm not sure. But the only thing that I see now, we want dy dx by itself. Let's multiply both sides by y. And when I write y on the right-hand side, I'm going to use what y is in terms of x. So we just found our derivative, dy dx is equal to 1/3 of 1 over x plus 1 over x plus 1 plus 1 over x minus 1 minus 1 over x squared plus 1. Oops, that would be a 2x minus 2x over x squared plus 1 minus 2 over 2x plus 3. all times y, but y was that cubed root of x, all times x plus 1, x minus 2, all over x squared plus 1, all times 2x plus 3.
Professor, where'd you get 1 over x minus 1, the third one? Because isn't it 1
That
over...
should be 2. That should be 2, right? X minus 2. Thanks. Anything else? So look how that wasn't too bad. I mean, if you knew the properties of breaking down your log and then knowing how fast the derivative of a natural log is just 1 over itself times the derivative of the inside, not of itself, but of what you're taking the natural log of.